Of the experimental seminar and the PhD defense of Kellen Myers.
Woohoo!
Thanks, everybody. The PhD defense will be a one-time seminar. So let's hope. So here is, I think, a different version of the abstract than what's online. Although, if you read what's online, congratulations. You don't need to know much to get started with this topic. I'm basically just going to give a few rudimentary sort of definitions and basic concepts. I'll talk a little bit about the existing work in this area, and then talk about what I've done. So, sort of the usual three-step. That's what this says. More words for those of you who like reading. So, we'll start with probably the two most basic definitions. An R coloring of S, which for now could just be any set, is a function from S to the set bracket R, which is just 1 through R. So R coloring because R is the number of colors. And just to be clear, when I say 1 through R, that is a finite number of colors. I don't think anything we say today would work if that were not the case. And with all of these things as above, some subset of S is called monochromatic if the number of colors assigned to it, say that set is S prime, is 1. So monochromatic. And we'll start with sort of the very first theorem in this area. In 1916, Schur proved that for any R coloring of the positive integers, there's a monochromatic solution to the equation x plus y equals z. Okay. And let that sink in. It doesn't seem like it's an especially interesting theorem on its own, maybe. Schur did not prove this because he thought this was interesting. He proved this in an attempt to prove something else, which was Fermat's last theorem. You may be aware that he did not prove it. Somebody else did. So, what's interesting to me is that you can sort of make a finite version of this statement. And a lot of statements could be phrased in one of two ways. Here, I have a pointer, why don't I get it? Here I have just positive integers. I don't care which ones or how many, I'm coloring all of them. Here, what I can say is if I limit my coloring from 1 to n, this statement will hold for n sufficiently large. And the question is, how far do I really have to go? And welcome to the latecomers. And in this case, these are called Schur numbers because this is Schur's theorem. And in the OEIS, there are exactly 4 of them, which is one of the shortest sequences. Probably not the shortest, Neil. No.
Don't you need 5 to get a cutoff? Don't you need 5?
It depends on the characters.
Yeah. So I suppose this is worth making an exception, no matter what the limit is. These 5, or these 4, are relatively interesting. But those are Schur numbers. Schur himself
proved some version of Fermat's theorem. Mod P or something?
He proved something similar to it, mod P, but of course, as some people in the room can tell you, there's a difference between mod P and regular. So I don't think what he did really got too far. I think this was something he sort of proved. It was interesting, but he set it aside, which is where we pick up Rado's theorem. So here's the same, it's repeated, and this I wrote ditto because I don't want to write the same thing twice. And what Rado said was, what if I take any linear homogeneous equation with integer coefficients, and the answer is that this is true for that equation if and only if a subset of the coefficients sum to 0. I guess I didn't write it, I probably should have. That subset should not be empty. But I think you know that that's true. So if you look at this equation, the x plus y equals z, the coefficients, if you move them all to one side, are 1, 1, and minus 1. Right? So if 1, 1, and minus 1 are the AIs in this case, then 2 of the 3 of them, if you choose carefully, sum to 0. Does this make sense to everybody? So here are some photos of these nice guys. We'll take a minute to say something about the history. So sure, I mentioned his theorem was proved in 1916, and there was a date on that last one. It was 1933. So what happened basically was when Shor proved his theorem, I don't think he called it a theorem, I'm pretty sure he just called it a lemma, and then tried to prove Fermat's last theorem and did not do so. His student, his PhD student, Richard Rado, said, what can I do with this to make it more interesting? And that's what he did. So, in some sense, Shor is the one who first planted the seed of this idea. But Rado, of course, gets a lot of credit for really showing that there's more to say here than just one off theorem. So, what we're going to do is talk about Rado numbers. And Rado numbers are the minimum n for a particular equation E and a particular number of colors R. So these Shor numbers for R colors are just the Rado numbers for that particular equation. And Rado showed that this works for lots of other equations. But in our mind, we could put any equation here, any number of colors here, and try to decide, can we find this number, and if so, what is it? So that's our goal. Our goal is to compute, or give a bound, or just say something about these Rado numbers. We can choose something that's kind of typical, or something that's kind of atypical. And I'll discuss both of those in a little while. For now, we'll sort of speak generally still. We'll say an equation has a Rado number, that it exists, if this number is, if it's sort of possible to do that. If not, we'll say it's infinite. And even if I say it's infinite, I might also say it doesn't exist, because as we know, infinity doesn't exist. So here's just one example of something that's maybe innocuous looking. So x plus 2y equals 4z doesn't seem to be particularly scary in any way. But for 3 colors, the Rado number doesn't exist. Okay. So we'll call the equation R regular if the number is finite. So this, for example, is not 3 regular, because it's not finite. And if we just say regular without specifying a number, it's because it's true for any R. So if we rewind to Shor's theorem, which I guess I can do if I click a lot, Shor's theorem says that this equation is regular, because it holds for all R. And for a fixed equation, we can sort of turn this definition around. The degree of regularity of a particular equation is how many R's you can say it's regular for. So here, it's not 3, as it turns out it's 2 for that particular equation. Whereas for this one, the degree of regularity is infinite, because you can do it for any R. So those are just general terms that we're going to use sporadically throughout the talk. And just to convince you that they're meaningful, in 2009, extending some work of a few other people, Alexeyev and Zimmerman proved that there is an equation that is exactly R regular. Its degree of regularity is R. And it's not a weird example. It's a linear homogeneous equation. And what that tells us is that these distinctions are meaningful. They're not just made-up categories that are all equal, which it'd be interesting if you could prove they were, but this tells us that you can't prove that. Here are just a few examples. I'll let you stare at them for a moment before I say anything. So here the first example is the third Shor number, so 3 colors, x plus y equals z, and that's 14. The next one is just something I made up, and the number is 7. Here is a relatively trivial example, which kind of shows you that there are a few equations that are not even 2 regular. And this was the example from before, where I said that it was exactly 2 regular, its degree of regularity was 2. Here the number is 4, which is not large or surprising, and it jumps straight to infinity if you add one more color. questions about these examples?
What are the two colors for the second and fourth case? Examples?
So for the second one,
No, what about it?
this one. Off the top of my head, I'm not going to be able to tell you.
Okay.
So I'm going to talk in just a few minutes about how most of what we're going to talk about in this talk is done by computer, which means even for something as simple as 7, which is not, you could do that as a human computer. But I didn't. I did it using a computer. So I don't know off the top of my head exactly what the colorings look like.
What about the fourth one?
The fourth one, I don't know. I don't think it would add much to take the time to show you, but I can show you after if you'd like.
So is it clear that one source of 3 is infinite, that afterwards is
Yes. I don't think I've said it yet, although maybe I could have. So if you add another color, the Rado number has to go up. Because, oh yeah, I'll speak to that more in a minute, but the idea is you would be able to color more things by having more colors, so automatically. It's not strict, it's not necessarily strict, but it can't decrease. So once you've hit infinity, it stays infinity.
Sorry to beat a dead horse, but do you know the coloring that shows for the third
Yes.
bullet point?
That's the one I thought you were asking. So here, this is the only one I'm prepared to say off the top of my head. Here, the way you do it is you color red, anything, so you factor all the integers simultaneously with your quantum computer or whatever. And anything where you look at the exponent on the 2, you color it based on whether that exponent is even or odd. Because then any solution you try to plug in would have to have one from one of those groups and one from the other. Does that make sense? Yeah. So it's almost like coloring odd and even, not quite. It's coloring based on odds or how even you are. Right? So if you're oddly even or you're evenly even.
Parity of the exponent of 2.
Yes.
Yeah. Anything else? Okay, so here's a repeat of another, I keep repeating things, so read it again if you like reading. So this theorem tells you whether this equation is regular. And it's necessary and sufficient, so that it exactly tells you that. Rado has a different theorem, which comes from the same, it comes from his thesis. It says any reasonable equation is too regular. And here, what I'm saying is of this type. So if I look at this equation, and I have at least 3 variables, and I'm not cheating and saying I have variables with zeros in front of them, then as long as some of my coefficients are positive and negative, it works for 2 colors. And I think you can convince yourself, if all of the coefficients here are positive, or if all of them are negative, then there are no solutions, which is silly. And if m equals 2, then we're in a case like this one, and you can pretty much decide, based on a similar argument, this will be infinity unless the coefficients are equal, in which case it will just be 1, because the solution 1, 1 immediately gets it. So this is where we get a lot of room to do computing. This is where, if you don't know what else to compute, and you have a computer, which we all do nowadays, if you were to ask the computer to do this, you would want to give it, naively, an equation that meets these conditions, because that gives you a safety. There's no concern that you might accidentally try to compute an infinite quantity. The last definition we're going to make, we'll start with a different example. So here's Ramsey's theorem, which I know a lot of you in the room are already familiar with. Ramsey's theorem is a very different context, but a very similar result, talking about graphs. You have a complete graph on some large number of vertices, and you color those edges, you get a monochromatic complete subgraph. And when Ramsey's theorem is proved, usually it's easier to prove if you don't care whether the 2 subgraphs that you're looking for the same size. So K1 and K2, you would get a K1 of color 1, or a KK1, or a KK2 of color 2. And that definition makes the proof easier. And that's generally something that you just sort of always consider these two parameters. Even if you consider them equal, you would just write R55, for example. And maybe R55 is more interesting than R44, but R45, right? R45 has a difference, but R45 is also pretty interesting. So what we can do is take that same idea where here we're associating just a number, K1 or K2, to color 1 or color 2. And we'll associate a different equation to each color, because that's our parameter. Our parameters are equations. So for 2 colors, we can say if E1 and E2 are 2 regular, which just requires them to have 3 variables and nothing silly, then we can find an off-diagonal Rado number, which has the same kind of look as those Ramsey numbers. So E1 goes to color 1, E2 goes to color 2. If you flip them, it's the same because you just switch the roles of the colors. But this only works, as far as we know right now, for 2 colors. So if I gave you 3 equations, and I said color 1 goes with this one, color 2 goes with that one, color 3 goes with that one, I could try to get the computer to do it, but we don't necessarily have a corresponding theorem that gives us that kind of safety. One of the reasons we don't do that is because Rado doesn't have a theorem to tell us about the 3-color Rado numbers, right? He said for all R or for 2R. He doesn't know about in-between. But we can define it this way, and here are a few examples which are a little more difficult to parse, so look for the semicolons. This one, x plus y equals z, that's one we're familiar with. And then the next equation, we just added an extra term. Second one is just a different example. And the last one, again, x plus y equals z, x plus y equals z, and then the same equation as above. So we can assign the same equation to 2 of the 3 colors if we want. This is to color 1 and to color 2, but something else is assigned to color 3. And that's okay. If they were all the same, then it would sort of collapse trivially into our previous definition. One thing, of course, that's important, what almost caught me, is I had a typo here. This number here, 3, has to match the number of arguments. I had a 2 there, but I caught it. So,
So the first one you can easily do by brute force.
Yeah.
Tape and pencil.
you could if you
The
wanted.
second one with the computer.
No. Yeah, that was,
To the power 43.
yeah, that was done by computer.
Yeah.
And so is this one, I think.
But if you do it by brute force, it's 3 to the power 26. You can do that.
Yeah, and when you increase the number of colors, sort of the base of the exponent, if you think of it as a brute force problem, gets bigger, which is very bad. So these are the sure numbers. We talked about those again. This is where we start. So I'm going to give sort of a laundry list of things that have been proved. I think I have a few notes on some of these. So these are sure numbers. I skipped the trivial 1-color case, which I'll do a lot. The 5th one is not known, and despite all the other things I can do, I can't say anything about that. I hope to one day, but not today. Which is surprising, I guess, considering how long ago, 50 years ago, the previous one was discovered. Here are a couple examples, sort of early examples. These are all linear equations. These are all 2 colors, so we know these have to be finite, and what these guys did in each case was just prove it. All of these are polynomials, which is somewhat interesting. A couple more examples, and these examples come together, which explains this one coefficient here. Because if you look carefully, all of these have sort of a similar pattern. So x plus y plus kz equals 1w is basically k squared over 1. Here, if I change this to a 2, it's k squared over 4. Here, if I change it to a 3, it's k squared over 9. And I can tell you experimentally that this pattern persists, but proving it for all values of this green number has so far been elusive, but at least I can give you a big grid of numbers and ask you to trust me. A quasi-polynomial, for those of you who don't know but might be interested, is something that takes polynomial values periodically. So I might have some... That's not what I mean. It takes the values of a fixed number of polynomials repeating. So it has 5 polynomials, and as you go, you plug into each one over and over again, depending on your modulus. Some more results, and this paper, despite coming on my 3rd slide of old results, is one of the first, if you notice the dates, 82 is one of the first other results in this area. Not a lot is different here, right? 2 colors, x1 plus x2. The only thing that's different between this and the 2 color Shor number is they've added arbitrarily many terms. Okay, and this is the formula for that. These 2 guys here and then these 2 guys here. Generalize that to virtually anything, not virtually, literally anything you want on the left-hand side. But this sort of fundamental result is one of the first past Rado. So there were other results that didn't really concretely discuss actual Rado numbers, and this is one of the first that does that. And we'll talk about these later. These are called generalized Shor numbers, which is just a type of Rado number, but it's one of special interest. People seem to be most interested in that. Here are a few more that are kind of interesting. So here people started playing with what's on the right-hand side. And again, there's sort of a pattern where this 2 just winds up in the denominator, just like this A also winds up in the denominator. And these are also quasi-polynomials, even though I haven't written them that way. And the use of the ceiling function is sort of why quasi-polynomials come up. Because depending on whether m is even or odd, it takes a slightly different value. There are some non-homogeneous equations that we can talk about. This, for example, is just Shor's numbers plus c, and it depends on whether c is positive or negative, but that got solved. And in fact, generalized Shor numbers also similar. So if you set c equal to 0 here, we recover m squared minus m minus 1 from 2 slides ago. If c is odd and m is even, then there's some parity problem and it's just infinity. So you do have to watch out for those issues. Here's a different case that's sort of presented for diversity, where now we have a coefficient that's not 1, because all of these were boring in that sense. I'm actually going to skip that because I'm a little short on time. It's not quite related to what we want to talk about. Nonlinear equations haven't been studied much. And this is something I've been working on for a while. And in the meantime, other people were working on it and proved things, fortunately, that weren't what I was doing. But were sort of the same type of problems. So here are a couple results where we've completely shed any belief that we could do a safe problem where we know the number is finite. None of these are linear equations, so nothing Rado says applies to them. But they still managed to compute these numbers, find a pattern, prove a theorem in all of these cases. So here and here, it should be pretty evident that they're taking previous results and adding some kind of exponent. X plus y plus equals z, just add an n here. X plus y plus c equals z, just add a 2 here. So these are the only results of this type that I have been able to find. The previous slide was something different that I'll brush under the rug to save a little time. So the one thing I'm going to try to say that's theoretical in nature is something I call collapsing variables. If I take an equation and I set 3 of the 8 variables equal to each other, I get a different equation with fewer variables. And what happens is that I use this preceding relationship here to denote that, and that is compatible with Rado numbers being less than. And the reason is any solution to the new equation has to be a solution to the old equation, where all those variables happen to be equal, but that's okay. So whenever I shrink the number of variables by doing this, I increase the Rado number, potentially to be infinite. So could be that I go from something reasonable to something not reasonable. And here's an example where I've sort of decided that this equation here is less than that equation there, and the Rado number sort of bears that out, because 4 is less than 9. So it's a partial order. It gives us some relationship that we can sort of use to our advantage. And what I've got now is a picture of not all of the possible results anyone has ever proved, but a fair number of them. So right at the top was the sort of trivial case, ax equals by. All the way at the bottom are sure numbers. There's nothing nonlinear, there's nothing non-homogeneous on here. There are still a few that are linear and homogeneous that aren't here. But to give you some idea, this was that really interesting result where the left-hand side could be anything. This was the interesting result where the right-hand side could be just one thing, but with any coefficient. And so up here is the unknown combination of those two. And there's a preprint that came out about a month ago, which I didn't really have time to read since I was busy. And I think it solves the problem for all of these. So this might not be open anymore. So don't go home and do it. There is a lot of room for improvement in this area. This is where I think there's more that we can get done. So I'm going to just say a little bit about how these numbers are proved and then talk about what we've managed to prove. So to make a lower bound, what you do is you exhibit a coloring which I'll call valid, which has no solutions that are monochromatic. And that means the Rado number has to be at least as big as that plus 1. So that seems relatively easy in the sense that if I give you this coloring, you can check it yourself. We can agree right away whether that's true or not. Upper bounds are a little bit more elusive. Very frequently, variables are collapsed, which could only increase the Rado number, which means any upper bound you obtain is still valid. And frequently the proofs are either just sort of a direct proof that the coloring could not be that long, or sort of a chasing down a contradiction proof, where you assume it's valid, and then you argue that 3 has to be blue, but 8k minus 7 has to be red, and therefore 8k minus 7 also has to be blue. Contradiction. I left out a lot of steps because I made that up. But the idea is that you just sort of argue by contradiction that it just could not be valid if it were that long. So here's a short example. So for a lower bound, all I have to give you is a 2 coloring of 1 through 4 that's valid. And if you check, this should work. There are no red solutions to x plus y equals z, and there are no blue solutions to x plus y equals z. To argue the upper bound, I have to do more than just show you a thing. So what I'll do is I'll assume that 1 is red. And I'll say, assume that I have a valid coloring of 1 through 5. Well, then 2 has to be blue. If not, 1, 1, 2 would be a monochromatic solution. But then 4 has to be red. And if 1 and 4 are red, then 3 has to be blue, and then 5 has to be red, and then 5 also has to be blue. And after that, all bets are off, because nothing makes sense. So we can try to construct these lower bounds using random methods, algebraic methods, guessing some pattern.